Imagine that something could exist which, if you fell into it, the universe would continue without you, not because you died, but because time itself would slow, stretch, and finally stop, leaving you suspended at the edge of forever while everything outside raced ahead billions of years. The strange part isn't the dying. The strange part is that from the outside, no one would ever see you cross that edge. You would be frozen there, a ghost at the threshold, growing dimmer and redder and slower until you faded like an old photograph. You would vanish not with a bang, but with a whisper, and the universe, entirely indifferent, would carry on now. Lie back. Let the darkness settle around you. Right now, as you breathe in this room, somewhere out there, in a galaxy so far away that its light has been traveling toward us since before the Earth had continents, a star more massive than 1,000,000 suns is dying. And when it dies, it will leave behind something so extreme, so alien to everything we understand about space and time and matter, that the best minds of the last 2 centuries have spent entire lifetimes just trying to describe it. Not explain it, just describe it. And they still argue about what it means. Tonight, we're going to take that slowly. We're going to walk through everything that is confusing about black holes. Every paradox, every piece of history, every brilliant person who stood at a chalkboard and said, "Wait, this can't be right," and find out that actually all of it is right. And that's exactly what makes it so beautiful. So close your eyes or let them drift. The room is quiet. This is a long, slow walk through one of the strangest ideas the human mind has ever encountered. Let's begin at the beginning. Not with Einstein, not even with Newton, but with a man sitting in a country rectory in 18th century England who had a thought so strange he barely knew what to do with it. His name was John Michell, and in 1783, he was the rector of Thornhill in Yorkshire. He was also, in his spare time, one of the most quietly brilliant scientists in England. He had already, before this moment, invented the torsion balance, the device that would later be used to measure the gravitational constant. He had done pioneering work in seismology, becoming one of the first people to apply mathematical reasoning to earthquake propagation. He was the kind of person who made enormous contributions to science, and then was largely forgotten because he was modest, because he published rarely, and because he lived far from London and its salons of scientific fame. He deserved more recognition than history gave him. In some ways, the story of black holes begins with an injustice. But in 1783, Michell wrote a paper for the Royal Society in which he proposed something almost incomprehensible for his era. He was thinking about light. Newton had proposed that light was made of particles, tiny corpuscles. He called them, and Michell accepted this. And if light was made of particles, then gravity should act on it. You can see where he was going. He asked, what if a star were massive enough and dense enough that the escape velocity, the speed you would need to travel to escape its gravitational pull, exceeded the speed of light? What if light itself, thrown upward from the surface of such an object, could not escape? It would rise, slow, stop, and fall back. The star would be invisible. A dark star, he called it. Think about that for a moment. In 1783, before the germ theory of disease, before electricity, before the railroad, this man was describing, in rough conceptual outline, a black hole. He was sitting in a rectory in Yorkshire, writing about the end of light, and he got it essentially right, using entirely the wrong physics. He calculated, using Newton's equations, that a star with the same density as our sun, but roughly 500 times its diameter, would have an escape velocity greater than the speed of light. He published this idea, and then, almost completely, history forgot about it. The French mathematician Pierre-Simon Laplace proposed something similar in 1796, also briefly, also quietly, in a footnote to a popular astronomy book, and then removed it from later editions, perhaps because he himself became uncertain about its validity. And then, the wave theory of light replaced Newton's corpuscular theory, and if light was a wave rather than a particle, it wasn't obvious that gravity would affect it at all. And the dark star idea sank beneath the water and stayed there for more than a century. It would take a revolution in physics to bring it back, and that revolution arrived in the person of Albert Einstein, though he himself didn't know, at first, what he had unleashed. Einstein was 26 years old in 1905, working as a patent clerk in Bern, Switzerland, and in the span of a single extraordinary year, he published 4 papers that changed physics forever. The one we care about tonight, well, the first one anyway, was his special theory of relativity. In it, he showed that the speed of light in a vacuum is the same for all observers, regardless of how fast they are moving. And from this single postulate, extraordinary consequences followed. Time slows for objects moving at high speeds. Mass and energy are equivalent. The most famous equation in science, E equals mc squared, falls directly out of this. Space and time are woven together into a single fabric that physicists call spacetime. But special relativity dealt only with objects moving at constant velocities. It said nothing about acceleration, and therefore nothing about gravity. Einstein knew this was a gap, and he spent the next 10 years trying to fill it. He later described a moment, in 1907, as the happiest thought of his ani fat of his life. He was sitting in the patent office when he imagined a man falling freely from a rooftop. During the fall, the man would feel no gravity. He would be weightless. Einstein realized that free fall and being in empty space far from any mass were, in some deep sense, the same thing, that you could not tell the difference between them from the inside. This is the equivalence principle, the conceptual bedrock of what would become general relativity. It took him nearly a decade to work out the mathematics, the equations he needed, the tools to describe how matter curves spacetime and how curved spacetime tells matter how to move, were tensor calculus, a branch of mathematics he had to learn essentially from scratch with the help of his dear friend Marcel Grossman, a mathematician who had taken better notes than Einstein during their university lectures. The two of them worked together in a collaboration that was one of the great partnerships in the history of science. The path was not smooth. Einstein made wrong turns. He published a version of the theory in 1913 that was incorrect, one that failed to satisfy the very symmetries the theory needed to have. He revised and revised again. There were moments of deep discouragement. There was also an embarrassing episode in which he and the mathematician David Hilbert were in a race to complete the correct equations, a race whose details have been disputed by historians ever since. And then, in November of 1915, over the course of 4 extraordinary weeks in Berlin, he completed the general theory of relativity. He submitted the final correct field equations on the 25th of November, 1915. They describe the universe with a compactness and elegance that physicists still find breathtaking. A set of equations relating the curvature of spacetime to the distribution of matter and energy within it. Gravity, in Einstein's view, was not a force at all. It was geometry. A massive object like the sun curves the spacetime around it, and the Earth, following the straightest possible path through that curved spacetime, traces out what we call an orbit. The planets don't fall around the sun because they're pulled by a force. They fall around it because the shape of space near the sun guides them along a curved path, the way a marble rolls around the inside of a bowl. Einstein submitted these equations, and then, as scientists do, waited to see what others would make of them. He did not have to wait long. Karl Schwarzschild was a German physicist and astronomer, and by 1915, he was one of the most respected astrophysicists in Europe. When the First World War began in 1914, he volunteered for military service. He was in his early 40s and under no obligation to serve, but he went anyway, out of what seems to have been a genuine sense of duty. By 1915, he was stationed on the Russian front, helping to calculate artillery trajectories. He was doing the mathematics of war with the same mind that, in other circumstances, he turned to the mathematics of the cosmos. And somehow, in this environment, he received a copy of Einstein's newly published field equations and began to work on them. In the winter of 1915 to 1916, while shells fell and soldiers died in the frozen mud, Schwarzschild found the first exact solution to Einstein's equations. He solved them for the simplest possible case: a single, perfectly spherical, non-rotating, electrically neutral mass sitting in otherwise empty space. What does space-time look like around such an object? The solution is beautiful, and it is troubling. It works perfectly at large distances from the mass. It reproduces Newton's gravitational law in the limit where gravity is weak, which is exactly what you'd want. But there is a specific radius, now called the Schwarzschild radius, at which something goes very wrong. At this radius, certain terms in the solution become infinite. The mathematics breaks down entirely. Something at this particular distance from the center of mass becomes undefined. Schwarzschild sent his solution to Einstein from the Russian front in a letter. Einstein replied, genuinely astonished and moved, writing that he had not expected anyone to be able to solve his equations in exact form so quickly. He presented the paper to the Prussian Academy on Schwarzschild's behalf in January of 1916. 2 months later, Karl Schwarzschild was dead. He had contracted a painful autoimmune skin disease called pemphigus while serving on the Eastern Front, and he died in May of 1916 at the age of 42. He never knew what the strange singularity in his equations meant. He never came home from the war. He left behind his solution, which would wait nearly half a century before anyone truly understood what it was saying. The Schwarzschild radius, the radius at which the math broke down, was initially dismissed by most physicists as a mathematical curiosity, a pathology of the simplified model. Surely, they reasoned, nothing in nature could actually be compressed to such a tiny size. The Schwarzschild radius of an object the mass of the Earth is about 9 millimeters. A marble. The Schwarzschild radius of the Sun is about 3 kilometers. No physical process, it seemed, could compress a star to that size. Einstein himself believed the singularity was unphysical, an artifact of the idealized mathematics, not a real prediction about the universe. He wrote a paper in 1939 arguing that a cluster of particles orbiting one another could not actually collapse to within the Schwarzschild radius, and therefore these objects could not form in nature. He was wrong, but his conviction delayed serious investigation into what the Schwarzschild radius actually meant by at least a decade. But we're getting ahead of ourselves. Let's slow down and spend some time in the 1920s and 30s, because this is when the human stories get particularly extraordinary and particularly painful. There was a young Indian student named Subramanian Chandrasekhar, and in 1930 he was 19 years old. Sailing on a steamship from Madras to Southampton on his way to study at Cambridge, he was a prodigy in every sense. He had already published papers on quantum statistics and stellar structure, and he was fluent in the most advanced physics of his day. He was also young enough, and perhaps confident enough, to think about problems without knowing in advance that they were supposed to be intractable. On that long ocean voyage, weeks of nothing but sea and sky, he had nothing to do but think. He was thinking about white dwarfs, the dense remnants of dead stars. It was already known by 1930 that when a star runs out of nuclear fuel, gravity causes it to collapse. For stars of roughly the sun's mass, the end state is a white dwarf, an extraordinarily dense object, roughly the size of the Earth, in which the electrons in the stellar material are compressed so closely together that they resist further compression through a quantum mechanical effect called electron degeneracy pressure. This pressure, arising not from heat, but from the fundamental quantum mechanical reluctance of electrons to occupy the same state, holds the white dwarf up against gravity indefinitely. On his ship, Chandrasekhar began doing calculations. He was combining the theory of white dwarfs with Einstein's special relativity, specifically accounting for the fact that the electrons in very massive white dwarfs would be moving at close to the speed of light, which changes their behavior in subtle but important ways. And what he found working through the mathematics alone in a cabin on the Indian Ocean was something extraordinary and deeply unsettling. Below a certain mass, a star could settle into a stable white dwarf. The electron degeneracy pressure would be enough to hold gravity at bay. But above a certain threshold, he calculated it at approximately 1.4 times the mass of the Sun. The electron degeneracy pressure was not enough. Gravity would win. The white dwarf could not exist. A star more massive than this limit, when it died, could not become a white dwarf. It would have to collapse further into something else. But into what? He did not yet know. But he had found what we now call the Chandrasekhar limit. And it was the first rigorous mathematical argument that sufficiently massive stars, when they die, have no stable resting place, that they might collapse without limit. He arrived in Cambridge and spent years refining the calculation. By 1935, the work was complete. He presented it to the Royal Astronomical Society in London in January of 1935. And here is where the story becomes painful in a way that is hard to read even now. Sir Arthur Eddington was the most eminent British astrophysicist of the age. He was 62 years old and at the peak of his authority. He was the man who had organized the famous 1919 solar eclipse expedition that confirmed Einstein's prediction about the bending of light, the experiment that had made Einstein world famous overnight. Eddington was a figure of towering intellectual prestige, a gifted writer, a brilliant mind. He was also, in this instance, entirely wrong, and his wrongness would cost Chandrasekhar decades. At the very same meeting where Chandrasekhar presented his findings, Eddington stood up and publicly ridiculed him. He said, "There must be some natural law preventing stars from collapsing without limit." He found it inconceivable that a star could collapse to a mathematical point. He called Chandrasekhar's conclusion an example of stellar buffoonery. He was not making a scientific argument. He had no mathematical objection. He was expressing a deeply felt personal conviction that the universe could not possibly behave this way, dressed up in the language of authority. And because Eddington was who he was, people listened. The objection without mathematical content was enough, coming from his mouth, to cast a shadow over Chandrasekhar's work. Several other prominent physicists expressed similar unease. Chandrasekhar, 24 years old, brilliant, devastated, found himself in an impossible position. He could not simply dismiss the most powerful voice in British astrophysics. He tried for a time to continue. He wrote papers. He made the arguments again. But eventually, discouraged and exhausted, he shifted his research away from stellar collapse and into other areas: stellar dynamics, radiative transfer, the theory of rotating figures. All important work, but not this. The Chandrasekhar limit sat in the literature, largely ignored, for nearly 2 decades. He received the Nobel Prize in Physics in 1983. He was 72 years old. In his Nobel lecture, he described the work on stellar structure that had begun on that ship in 1930, the work that had been dismissed and derided by Eddington. By then, the Chandrasekhar limit was recognized as one of the foundational results in astrophysics. By then, everyone knew that he had been right. By then, Eddington had been dead for 37 years and had never, to anyone's knowledge, acknowledged his error. The history of black holes is full of moments like this. Brilliance meeting resistance, not because the mathematics was wrong, but because the conclusion was too strange, too extreme, too threatening to the intuitions of powerful people. The question that Chandrasekhar's work raised: what happens to stars more massive than 1.4 solar masses when they die? Would be partially answered by the American physicist J. Robert Oppenheimer and his student Arslan Snyder in 1939, in a paper published in September of that year, the same month the Second World War began. They showed, using general relativity, that a sufficiently massive star would indeed undergo gravitational collapse, and that from the perspective of a distant observer, the collapse would appear to slow and freeze at the Schwarzschild radius, and from the perspective of the infalling matter itself, the collapse would proceed past the Schwarzschild radius in finite time, into what lay beyond. They could not fully describe what lay beyond, but they had shown that the collapse was real, that general relativity predicted it, and that the Schwarzschild radius was not a mathematical artifact, but a real feature of the universe. Oppenheimer went on to lead the Manhattan Project. He became one of the most famous and tragic figures of the 20th century. He never returned to this work. The paper on gravitational collapse sat largely unread for years, partly because the war consumed everyone's attention, and partly because Oppenheimer himself never promoted it. But it was there, waiting. And here's where it gets interesting. While all of this was happening in theoretical physics, observational astronomy was beginning to reveal things about the universe that would eventually make black holes not just plausible, but necessary. Let's move to the 1960s, because by then, several threads were converging in a remarkable way. Radio astronomy, observing the universe not in visible light but in radio waves, was a young field in the early 1960s, but it was already producing strange results. In 1963, the Dutch-American astronomer Martin Schmidt at the California Institute of Technology was studying a class of objects that had been cataloged as strong radio sources. When he looked at one of them through the Palomar telescope, the object cataloged as 3C273. It appeared, in visible light, to be an ordinary faint blue star. Nothing remarkable, except that its spectrum was wrong. The absorption lines in its spectrum, the fingerprint-specific elements, were there, but they were shifted dramatically toward longer wavelengths, toward the red end of the spectrum. The redshift was enormous. Schmidt puzzled over this for weeks, and then, in early 1963, it clicked. The lines were the hydrogen-Balmer series shifted by about 16% toward the red. This was not a nearby star. This redshift meant the object was receding from us at about 47,000 kilometers per second, a significant fraction of the speed of light. And in an expanding universe, recession velocity corresponds to distance. 3C273 was at a cosmological distance, billions of light years away. But if it was that far away and still appeared as bright as it did from Earth, then, to produce that apparent brightness, it must be generating energy on a scale that defied comprehension. More energy than entire galaxies, from a region that, even through the most powerful telescopes, appeared to be essentially a point. Schmidt announced his findings in March of 1963. He coined the term quasi-stellar object, quasar, for this strange new class. There were soon found to be many of them. The question that quasars posed was urgent. What engine could produce so much energy from so small a volume? The answer, developed over the following years by a number of theorists, including Edwin Salpeter and the Soviet physicist Yakov Zeldovich, was gravity, specifically the gravitational energy released by matter falling into an extremely massive, extremely compact object. As gas and dust spiral inward towards such an object, they form a flattened disk, an accretion disk, in which the infalling material moves faster and faster, heats to temperatures of millions of degrees, and radiates prodigiously across the electromagnetic spectrum. The energy released per unit of infalling mass is far greater than that released by nuclear fusion. A spinning compact mass devouring surrounding matter is the most efficient energy source the universe contains. The compact object at the center had to be something that could fit into a region smaller than our solar system, but contain the mass of hundreds of millions, or even billions of suns. There was really only one candidate, what we were beginning to call a black hole. And here is where the name itself enters the story. For most of the early 20th century, these objects were referred to by cumbersome descriptions. Completely collapsed gravitational objects, frozen stars, gravitationally collapsed stars. Soviet physicists used the term frozen star because, from a distant observer's perspective, the collapse of a star to within the Schwarzschild radius appears to freeze. The infalling surface seems to halt at the horizon, growing redder and dimmer. The name was evocative but technically misleading about what actually happens. The term black hole was popularized by the American physicist John Archibald Wheeler. Wheeler used it publicly in a lecture in late 1967, and through the force of his personality, and his enormous influence in American theoretical physics, the name caught on immediately. Wheeler may not have been the very first person to use the phrase. The exact origin is somewhat uncertain, and Wheeler himself acknowledged in his autobiography that the term may have been suggested by someone in an audience. But he adopted it, repeated it, and made it the universal name for these objects. It was the right name. It is immediate, strange, and accurate in the way that the best scientific names are. Wheeler was one of the most important figures in 20th century physics. He had studied under Niels Bohr, one of the founders of quantum mechanics. He had worked on the Manhattan Project, playing a key role in the plutonium production reactors at Hanford. He had spent decades thinking about the foundations of quantum mechanics and its relationship to reality. And he had a gift for the kind of phrase that crystallizes a whole landscape of thought into a few words. He gave us black hole. He gave us wormhole. He gave us the summary of general relativity that is perhaps the most elegant single sentence in all of physics. Spacetime tells matter how to move. Matter tells spacetime how to curve. His students included Richard Feynman and Kip Thorne, and through them, his influence extended through the whole of late 20th century physics. Now let's talk about the event horizon itself, because it is one of the most confusing things about black holes, and it deserves real time. People often imagine the event horizon as a physical surface, like the surface of a planet, something you would see or feel if you approached it. It is nothing like this. The event horizon is not made of anything. It has no material existence. It is, in the most precise possible sense, a mathematical boundary, the surface in space-time at which the escape velocity from the black hole equals the speed of light. Inside this boundary, the escape velocity exceeds the speed of light, which means nothing, not light, not any signal, not any physical object, can travel outward, not because something pushes it back, but because the geometry of space-time itself no longer contains an outward direction. Think about that carefully, because it is worth sitting with. Normally, we think of space as having all directions available to us. We can go forward or back, left or right, up or down. We can move toward a massive object or away from it. Inside a black hole's event horizon, this is no longer the case. The singularity at the center is not in a direction. It is in the future. Every world line, every possible path through space-time, leads toward it, the way all paths through time lead toward tomorrow. You cannot escape the singularity inside a black hole. For the same reason, you cannot escape Tuesday. It is not in any direction. It is simply what comes next. Now you might ask, if the event horizon is just a mathematical surface, would you notice crossing it? And the answer depends enormously on the size of the black hole. If the black hole is small, a few times the mass of the sun, with an event horizon only a few kilometers across, then the tidal forces near the horizon are catastrophic. Tidal forces are the difference in gravitational pull across a body. The moon creates tidal forces on the Earth. The side of the Earth closer to the moon is pulled a bit more strongly than the far side. And this difference is what causes the tides. Near a small black hole's event horizon, this tidal difference across the length of a human body becomes enormous. Billions of times the force of Earth's gravity, applied differently to your head than to your feet. You would be stretched out into a long, thin strand of matter. Physicists call this, with characteristic humor, spaghettification. This is the actual technical term. It appears in the peer-reviewed literature. You would be spaghettified long before you reach the horizon. But a supermassive black hole, one with billions of solar masses and an event horizon billions of kilometers across, is a different story entirely. The tidal forces at such a large horizon are actually quite gentle. You could cross the event horizon of the black hole at the center of a large galaxy and feel nothing unusual at all. No wall, no barrier, no alarm. You would simply be inside, with no way back, with the singularity as your future. While outside, the universe continued for billions of years without you, and from the perspective of someone watching you fall in, safely, from a great distance, they would see something else entirely. This is where the strangeness of general relativity becomes almost vertiginous. Gravity slows time. This is not a metaphor. It is a measurable, tested, confirmed fact. Clocks in stronger gravitational fields tick more slowly than clocks in weaker fields. This is called gravitational time dilation. And it is real enough that the GPS satellites in orbit above the Earth, where gravity is weaker, tick slightly faster than clocks on the ground, by about 45 microseconds per day. Engineers correct for this difference. Without the correction, GPS would be useless within hours. Near a black hole's event horizon, gravitational time dilation becomes extreme. As your infalling friend approaches the horizon, their clock appears to run slower and slower from your distant vantage point. Their image appears to dim and redden as the light they emit has to do more and more work to climb out of the gravity well, losing energy, shifting to longer wavelengths. Their movements slow, and in the mathematical limit, they appear to freeze at the horizon, never quite crossing, growing ever dimmer, eventually redshifting beyond the visible spectrum into infrared, then microwave, then effectively invisible. From your perspective, they never fall in. They hover at the edge of forever. From their perspective, they cross the horizon in a finite time and continue inward. Nothing marks the moment of crossing. The stars above them would appear blue shifted. The universe outside, seen through a shrinking circle of light above them as they fall, would appear to speed up. And then they would reach the singularity. Two observers, two incompatible experiences, both simultaneously true. There is no God's eye view that reconciles them. General relativity is, in a deep sense, a theory of perspectives, a theory that insists that reality looks genuinely different depending on where you are in space-time, and that neither view is more real than the other. Now, in the 1970s, a young British physicist named Stephen Hawking found something that no one expected, something that changed everything. Hawking was working at the intersection of general relativity and quantum mechanics, two theories that are separately extraordinary and mutually incompatible in their foundations. General relativity describes the large-scale structure of the universe with stunning precision. Quantum mechanics describes the behavior of matter and energy at the smallest scales with equally stunning precision. And yet, when you try to apply both theories simultaneously to the same situation, they generate contradictions. A complete theory of quantum gravity, a theory that unifies the two, does not yet exist. Hawking was thinking about what quantum mechanics implies for the vacuum of space near a black hole's event horizon. And here is what quantum mechanics tells us about the vacuum. It is not empty. At the smallest scales, space seethes with activity. Pairs of particles and their antiparticles constantly flicker into existence and annihilate each other almost instantly, borrowing energy from the vacuum and returning it on timescales so short they cannot be directly observed. These are called virtual particles, and their existence has measurable effects. The Casimir effect, the Lamb shift, that have been confirmed experimentally to high precision. Now imagine this flickering vacuum near the event horizon of a black hole. A pair of virtual particles appears, straddling the horizon, one on each side. Before they can find each other and annihilate, one of them is swept inward past the horizon by the curvature of space-time. The other escapes outward into space as a real particle. From the perspective of a distant observer, this looks like the black hole is emitting radiation, a slow, steady trickle of particles emanating from the vicinity of the event horizon. Hawking published this result in 1974, and the physics community was stunned. Black holes were not black. They radiated, and the radiation had a temperature, now called the Hawking temperature, that depended on the mass of the black hole. The smaller and lighter the black hole, the hotter it radiated. For stellar mass black holes of a few solar masses, the Hawking temperature is fantastically small, a tiny fraction of a degree above absolute zero, far colder, in fact, than the cosmic microwave background radiation that permeates all of space at about 2.7 degrees Kelvin. This means that, right now, stellar mass black holes are actually absorbing more energy from the cosmic background than they emit via Hawking radiation. They are growing, not shrinking. They will not begin to evaporate until the universe has expanded and cooled enough to drop below the Hawking temperature of stellar mass black holes, which will take unimaginably longer than the current age of the universe. But here's the thing. If Hawking radiation is real, and almost all physicists believe it is, even though it has never been directly observed, because the theoretical argument is so robust, then black holes do eventually evaporate. Slowly, they lose mass. Slowly, as they lose mass, they get smaller. As they get smaller, they get hotter. As they get hotter, they radiate faster. The evaporation accelerates, and in the final moments, the black hole radiates away its last mass in a burst of high-energy particles and radiation. A final flash, and then it is gone. The scale for this process, for a stellar mass black hole, is something like 10 to the power of 67 years. That is a 1 followed by 67 zeros. The current age of the universe is about 13.8 billion years, roughly 10 to the power of 10 years. We are talking about timescales so vast they make the current age of the universe look like an instant. But the evaporation raises a profound question. And here is where we arrive at the deepest mystery in all of theoretical physics: the black hole information paradox. When a star collapses to form a black hole, it carries with it an enormous amount of information. Information about the quantum states of every particle that made up the star. What kind of atoms were they? How were they arranged? What were their momenta, their spins, their quantum numbers? In quantum mechanics, information is never destroyed. This is not merely a practical statement about our ability to track things. It is a fundamental law. The equations of quantum mechanics evolve the quantum state of a system in a way that is, in principle, perfectly reversible. Given the final state, you can always work backward to find the initial state. Information is conserved. But now consider what happens when the black hole evaporates. The Hawking radiation it emits is, to a very good approximation, thermal radiation. Thermal radiation is the radiation emitted by a warm body, and it carries almost no specific information about the body that emitted it. A hot coal and a hot iron glow with the same kind of light at the same temperature. You cannot tell from the light what the original object was made of. If the black hole evaporates entirely into thermal Hawking radiation, then all the information about what fell in has been destroyed. It is gone. The final state of the radiation does not encode the initial state of the infalling matter. And that is a direct violation of the fundamental principles of quantum mechanics. This is the information paradox. It is not a puzzle about practical information storage. It is a contradiction between two of our best theories of nature. Either quantum mechanics is wrong, which would be catastrophic, given how extraordinarily precisely it has been confirmed, or general relativity's description of black holes is wrong in some subtle way, or there is some entirely new physics that we don't understand yet. Hawking himself, for many years, believed that information was genuinely destroyed by black holes, and that this represented a real breakdown of quantum mechanics in extreme conditions. He was in the minority among physicists on this point. In 2004, at a conference in Dublin, he publicly conceded a bet he had made with Caltech physicist John Preskill, announcing that he now believed information was preserved and did escape the black hole, encoded in subtle correlations in the Hawking radiation. But the precise mechanism by which this could happen remained and remains deeply unclear. The debate produced a remarkable result called black hole complementarity, proposed by Leonard Susskind and his collaborators in the early 1990s. The idea is that from the perspective of an outside observer, infalling information is radiated back out in the Hawking radiation, preserved, just scrambled beyond any practical recovery. But from the perspective of the infalling observer, the information passes through the horizon intact, never to be retrieved by the outside world. Both descriptions are true. They are complementary in the quantum mechanical sense, and crucially, no single observer can ever see both pictures simultaneously. The outside observer can never enter the black hole to check, and the infalling observer can never send a signal back. So the contradiction never produces a measurable inconsistency. This is beautiful and deeply strange. The universe seems to be protecting its own consistency by making it impossible for any single observer to catch it in a contradiction. But in 2012, a group of 4 physicists, Ahmed Almheiri, Donald Merolf, Joseph Polchinski, and James Sully, often called AMPES after their initials, found a new problem. To preserve information in the Hawking radiation, the radiation emitted by the black hole at one moment must be quantum entangled, linked in the quantum mechanical sense, with the radiation emitted earlier. And the infalling particle at the horizon must be entangled with its virtual pair partner inside. But quantum mechanics has a rule called the monogamy of entanglement. A quantum system can only be maximally entangled with one other system at a time. A particle cannot be fully entangled with 2 different things simultaneously. Something must break. Either the entanglement that preserves information in the outgoing radiation is broken, in which case the information paradox is real and quantum mechanics fails, or the entanglement between the virtual particle pairs at the horizon is broken, in which case the pair production doesn't happen smoothly. Instead of empty, gentle vacuum at the horizon, there is a wall of high-energy radiation, a firewall. This firewall would destroy anything crossing the horizon, even gently, even in a supermassive black hole. And if there is a firewall, then Einstein's equivalence principle, the happiest thought, the idea that falling freely through a black hole's horizon is indistinguishable from floating in empty space, is violated. So the community faces a choice: preserve information or preserve the equivalence principle. The two seem incompatible. Pick which pillar of physics you prefer to keep. No one has resolved this. As of today, the firewall paradox remains one of the deepest open questions in theoretical physics. Physicists have proposed many potential resolutions, modifications to the structure of space-time near the horizon. The concept of fuzzballs from string theory, the holographic principle which suggests that the physics of a black hole's interior is somehow encoded on its two-dimensional surface, but none has achieved consensus. This is genuinely unresolved. The greatest minds in physics are still arguing. Let's step back now from the theoretical maze and into the observational triumphs, because the last decade has been extraordinary. For most of the history of black holes, they were theoretical objects. No one had seen one directly. All evidence was indirect. The behavior of stars and gas near what appeared to be a very dark, very massive, very compact object. This began to change in spectacular fashion. The first gravitational waves were detected on the 14th of September 2015 by the LIGO observatories, the Laser Interferometer Gravitational Wave Observatory, one detector in Livingston, Louisiana, and one in Hanford, Washington. The signal lasted about 0.2 of a second. Analysis showed it had been produced by two black holes, one approximately 29 solar masses, one approximately 36 solar masses, spiraling together and merging, about 1.3 billion light-years away. In that final fifth of a second of the inspiral, the system radiated more energy in gravitational waves than all the stars in the observable universe combined emit as light in that same period. That signal had been traveling through space for 1.3 billion years. It passed through galaxies and through the void between them. It crossed the Earth on that September morning, compressing and stretching space by an amount about 1,000 times smaller than the diameter of a proton, and LIGO detected it. The announcement came on the 11th of February, 2016. It was one of the greatest moments in the history of observational science. Rainer Weiss, Kip Thorne, and Barry Barish received the Nobel Prize in Physics in 2017. Humanity had, for the first time, heard the universe speak in a language other than light. And then came the image. In April of 2019, the Event Horizon Telescope collaboration released the first image ever made of a black hole's shadow. The Event Horizon Telescope is not a single instrument. It is a global array of radio telescopes spanning from Hawaii to the South Pole to the Spanish Highlands that were synchronized to observe simultaneously using a technique called very long baseline interferometry. Together, they formed a virtual dish the size of the Earth, capable of resolving features a fraction of the size of anything previously imaged in astronomy. They targeted the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away, with a mass of approximately 6.5 billion solar masses. And what they produced was an image, a bright ring of glowing orange plasma, slightly brighter on one side where the orbiting material is moving towards us, and its radiation is Doppler boosted, surrounding a dark central region, the shadow cast by the event horizon against the luminous background of the accretion disk. The shadow of an event horizon, light, unable to escape from a region of space, visible against the light that can. After more than 2 centuries of mathematics, thought experiments, arguments, and indirection, we had a picture. 3 years later, in May of 2022, the same team released an image of Sagittarius A star, the 4 million solar mass black hole at the center of our own Milky Way galaxy, about 26,000 light years away. It was technically far harder to image than Messier 87, smaller on the sky, more obscured by dust, and its accretion disk varies on timescales of minutes rather than years, making it difficult to assemble a coherent image from observations spread across nights. But the team succeeded. There it was, the black hole at the center of our own galaxy, glowing, dark-cored, patient, vast. Let's spend a few minutes on some of the most common misconceptions, because this topic attracts them. The first is that black holes are cosmic vacuum cleaners, actively sucking in anything nearby. They are not. A black hole, with the same mass as the Sun, would exert exactly the same gravitational force on Earth as the Sun does now. Our orbit would not change. The planets would continue as before. Nothing would be sucked in. The extreme gravity of a black hole is only extreme at close range, within the region where the original star used to be. The danger of a black hole is not that it is supernaturally hungry. It is that it is small enough to approach very closely, at which point you are inside a ferociously strong gravitational field, with no surface to land on and no force to stop you from falling inward. The second misconception is that the singularity is a real place inside the black hole, an actual point of infinite density at the center, like an infinitely sharp pin. Almost certainly, it is not real. The singularity, in the mathematics of general relativity, is almost universally interpreted as a signal that the theory has been pushed past its domain of validity. At the extreme densities and spacetime curvatures near the center of a black hole, quantum effects become important, and general relativity, which is a classical theory that ignores quantum mechanics, breaks down. What actually happens at the center may be something entirely different from a singularity. We do not know. We cannot know until we have a theory of quantum gravity. The singularity is not a discovery. It is an admission that our best theory does not apply there. The third is that time travel through black holes is a realistic possibility. There are solutions to Einstein's field equations, the so-called Kerr solution for rotating black holes, and various wormhole geometries that permit mathematically paths through space-time that could in principle allow travel to other times or other regions of the universe. Whether these solutions correspond to anything physically realizable, and whether they could be traversed by anything, remains deeply unclear. Most physicists believe that quantum effects and a principle called chronology protection, proposed by Hawking, likely prevent such paths from being stable or usable. But the honest answer is that we do not know for certain. And then there is this. The universe's black holes have a long future ahead of them, longer than anything we can comfortably imagine. When the last stars burn out, trillions of years from now, when galaxies have dispersed and ordinary matter has decayed, and the universe has expanded into near perfect cold darkness, the black holes will remain. They will be the last coherent structures in the universe, slowly, barely perceptibly evaporating. The supermassive black holes at galactic centers, with masses billions of times that of the Sun, may take something on the order of 10 to the power of 100 years to evaporate entirely. A Google years. The current age of the universe is about 13.8 billion years, roughly 10 to the power of 10. We are talking about the black holes outlasting the current age of the universe by a factor of 10 to the power of 90. In the deep future of the cosmos, the black holes are the final candles, and when they go in a burst of radiation. The last photons from the last evaporating black hole will travel through an empty, cold, dark universe, carrying with them, in subtle quantum correlations we do not yet know how to decode, the scrambled memory of everything that ever fell in. All the matter, all the stars, all the light that was ever swallowed. The universe's final act belongs to black holes. But here's what I find most moving about all of this. Lying in the dark and thinking about it. Every single piece of this understanding was built by human beings. Real, specific, fallible human beings. Michel, in his Yorkshire rectory with a quill pen. Chandrasekhar, on a steamship doing mathematics in the margins of notebooks. Schwarzschild in the trenches with shells falling. Einstein pacing the streets of Berlin. Hawking calculating in his head because he could no longer write things down. The engineers and scientists of LIGO, thousands of them, spending decades tuning mirrors and lasers to detect a ripple smaller than an atomic nucleus. The radio astronomers who pointed their dishes at a galaxy 55 million light years away and waited and computed and waited, and finally saw an orange ring of fire around a dark center. None of them could see a black hole. None of them could travel to one. None of them knew, when they began, what they would find. They were doing what humans do at their best, following a question because the question was beautiful, and because they could not let it go. They were extending the boundary of the knowable by one more step, adding one more lamp to the very edge of the dark. That is what science is, in the end. Not a collection of facts, a posture, a willingness to say, I do not understand this yet, but I will sit with it until I do. Black holes are what the universe looks like when you sit with the hardest questions long enough. They are the universe asking itself what it is made of. And the answer, so far, is something stranger than we imagined, and stranger still the deeper we look. The question rests now for tonight. You are here, in this room, in the quiet and the dark, and the weight of the blankets is a good weight. And somewhere unimaginably far away, so far that the light would take more than 1 billion years to reach this bed. Two black holes are spiraling closer to each other in slow, inevitable arcs. And one day they will merge and send a shiver through the fabric of spacetime, and that shiver will travel outward at the speed of light, crossing billions of light years of cold and dark, and perhaps someone, somewhere on some world still warm, will detect it, and will know that something vast happened long ago in the dark between the galaxies. The universe will have spoken. Someone will have listened. Let that thought drift now. You don't need to hold it. It will be there if you want it. The body is heavy and warm. The breath is slow and even. The thoughts are already softening at the edges, losing their definitions, the way ice loses its edges in warm water. The darkness in this room is the same darkness between the stars, the same quiet, the same depth, the same patience. You are made of atoms forged inside stars that died before the sun was born. For a little while, those atoms arranged themselves into something that could wonder about black holes, and now they are resting. The wondering can stop now. The breath, the warmth, the weight, quiet.